Algebra 1, Lesson 109. We are looking at our inequalities again, being able to graph those. But now we're going to have a system of linear inequalities, which means we're going to have multiple ones on a graph. Just like we would with our regular linear equations, we want to figure out what is the intersection. Okay, but there's going to be more than just one answer to this. So system of linear equations, we have two or more linear equations with the same variables. That's what we've looked at before, and we could have them intersecting, have them parallel, or even have the same line. Now the solution for the system is where two equations intersect. So if we had these two and we wanted to find the solution, we would graph both of them, and of course they're in slope-intercept form. So we could, if I were to do just a really quick graph right here, let me just make some space. So if I were to have my graph, say, we had x plus 1, well, that would have a y-intercept of 1 and a slope of 1. So up 1 over 1, up 1 over 1, and we have our line. Or we have y equals 2x, well, we have a y-intercept of 0, so we have right there, up 1 over 1, or sorry, up 2 over 1, up 2 over 1, and we have this line, which means they intersect right here at 1, 1, which when we plug that in, we do see that it does work. Okay, we plug in, sorry, that should have been 1, 2. 1, 2. There we go. Because when we plug it in, y is 2 is equal to 1 plus 1, and 2 is equal to 2 times 1. Okay, we're looking for that intersection point if we have our linear equations. If we have system of linear inequalities, this is a set of linear inequalities with the same variables. And the solution of the system of linear inequalities is an ordered pair that satisfied both inequalities. Okay, so very, very similar here, but we have lots of different options for our solution to the system of linear inequalities. So let's look at one in particular. So if I want to graph these, remember, I'm first going to graph them just like I normally would. So these are the same that I just had on the other page, except we need to think about what types of lines and how do we need to shade them. So I'm still going to have this first one having a y-intercept of 1 and having a slope of 1. Now since this is less than or equal to x, we can have a solid line. All right, and then we need to decide how we need to shade this. Well, I always like to plug in 0, 0. So I have 0 is less than or equal to 0 plus 1. Is that a true statement? Well, 0 is that less than or equal to 1. And yes, that is. So we shade towards 0, 0. All right, next line. We have a y-intercept of 0 and a slope of 2. So up 2 over 1, up 2 over 1, all the way through. And we saw that earlier. This point of intersection here at 1, 2 is where we would have just this linear equation answer, the system of linear equations. Here we're going to have more than just that. But we still need to shade this other one. So we would say 0 is less than or equal to 0, so 2 times 0, and that is a true statement, so we would include 0. Now that's on the line. So maybe I pick a different one. Let's say I pick this point right here, just to make sure I know where to shade. And that point is 0, 4. So I'd say 4, is that less than or equal to 2 times 0? No, it is not. That's not a true statement, so I'm not going to include that point, which means that I need to shade this way. Okay, I need to shade away. Now what you will notice here is that there are parts of this graph that are shaded 0 times, okay, like this region up here. There are parts that are shaded just once from a certain line, like here and like in this triangle. And then there's a region that is shaded twice. The region that is shaded twice is all of our solutions to this linear inequality. Okay, the system of linear inequalities can have any of those solutions. So this solution right here, this one up here is a solution. Okay, right here solution. And since these are both filled in lines, even where they actually intersect is a solution. Okay, So is 3, 2 a solution? Well, let's see. Up 3 over 2, it's in the 2 shaded region, so yes, this is a solution. Okay? We're looking for the region that is shaded twice from the graphs. So let's try it again. Graph y is greater than 1/4 x minus 3. So we do that. We say we have a y-intercept of -3 and a slope of 1/4. So up 1 over 4, up 1 over 4, or down 1, left 4. Down 1, left 4. Now this is a greater than symbol, which means that I have a dashed line across here. All right. Now I need to decide how to shade, so I plug in 0, 0. So 0 is greater than, 1/4 times 0 is 0, minus 3. So 0 greater than -3? Yes, it is. So I'm going to shade towards 0, 0. So this guy gets shaded up this way. All right, let me just erase that extra little bit of shading here. All right, and then we try again with our next inequality. Okay, and we say y is less than or equal to 3x plus 4. Now I'm going to do this in a different color just so it looks a little bit different. It's easier to see. So we have a y-intercept of 4, so up 4, and then we have a slope of 3, so up 3 over 1, up 3 over 1, down 3 left 1, down 3 left 1. And now this is a less than or equal to, so I have a full line here. Okay, now we need to decide how to shade. So I plug in 0, 0. 0 is less than or equal to 3 times 0 plus 4. Is 0 less than or equal to 4? Yes, it is. So I am going to include 0, 0. Okay, and now we can see where has it been shaded with both yellow and this purple pink, and it's in this region here, which means we have lots of different solutions there, including 0, 0. But we could say, is -2, 4 a solution to this? Let's see, -2, 4 is way up here. No, that is not a solution. Although it's a solution for the first inequality, it's not a solution to the second, which means it's not a solution to the system of inequalities. Okay? Has to satisfy both. All right, we'll just do a couple more of these. All right, y is less than 4. Well, y is equal to 4 would be a horizontal line at 4. And if I have it less than 4, that means that I have a dashed line at this horizontal line of 4. Oops, sorry about that. All right. Give me just a second to figure this out. All right, so we have this dashed line, and I'll make it pink here. Dashed line at y equals 4. And now we need to decide where it's shaded. So if I were to plot 0, 0, well, is 0 less than 4? Yes, it is. So I would shade underneath here. All right, let me try this next one. I'll just get rid of this extra so we're not confused by it. All right, and then for this next one, I'm going to transform this formula for a second here. And I want to get it so that y is by itself. It's a little bit easier if we do it that way. So we have 2y is greater than -6x minus 2. Divide by 2, and we get y is greater than -3x minus 1, which means that I have a y-intercept at -1 and a slope of -3. So down 3, right 1. Down 3, right 1, or up 3, left 1, up 3, left 1. Now we have a greater than sign, which means I need another dashed line for my green inequality. And we try and we plug in 0, 0. So that means for this one I would have y is 0 is greater than -3 times 0 is 0 minus 1. So is 0 greater than -1? Yes, it is. So we shade towards 0, 0. Which means we're going to shade this way. We're going to include 0, 0 in our graph, which means all of this part right here is the solution to our linear inequality, our system of linear inequalities. So is 4, 8 a solution? 4, 8 is way up here. So, although it's a solution to the green inequality, it is not a solution to the purple, which means that no, this is not a solution. Okay, so those are 3 examples that you can look at and try again. Here are a couple others that you can try. You could transform each of these into slope-intercept form, or you can put them into standard form. Either way will work pretty well. Okay, and then you can also use your graphing calculator to do this, and you can look back at a previous lesson about how to do that and how to shade correctly, whether that's by hand or using your calculator's functions to do that. But you can check these on your graphing calculator. Okay? And there's lots of different examples here that you can try, but another example that you could end up looking at is sometimes, just like our linear equations, a system of equations is inconsistent when there are no solutions. And this happens when the slope is the same, and therefore they don't intersect at any point. We've had this before. So, like these, we have the slope as the same, different y-intercepts, so we don't have a solution to this. Now, when we have a linear system of inequalities with the same slope, the system, it could actually have solutions, because we still could have shading that ends up being together, being on the same. But it doesn't always have to happen that way. So let's just try this one here. So with these ones, I'm just going to do this very quickly. Y-intercept of -2, and then we're going down to right 3, down to right 3. We have a full line here. Plug in 0, 0. We get 0 is less than or equal to -2. Is 0 less than or equal to -2? No, it's not. So we shade away from 0, 0. And we try the other one, a slope of 3, and we go down to right 3, down to right 3, full line again. All right, and then we say, is 0 greater than or equal to 3? Well, no, it is not, so we shade away, okay? So we don't include 0, 0 there again, and we see we don't have any solutions in common, but you can imagine if this were if this were a consistent inequality sign, we would have some shading going in the same direction. Okay, so we can see these types of situations as well. All right, and you can try this one as well, very similar. All right, and now we have the same inequality. See how that changes things when you graph them. And here are a couple word problems that you can try. Biggest thing here is make sure that your equations are actually representative of the situation. So we'll look at the first one together, and then I'll show you the second one so you can try it on your own. Lena has to earn at least $210 per week from 2 part-time summer jobs. She can work up to 15 hours per week at job A, which pays $12 per hour. She could also work at job B for up to 35 hours per week at $10 per hour. She's not allowed to work more than 40 hours a week. Graph the possible combinations of hours that she can work. Start by writing the system of linear inequalities using X as the number of hours worked at job A and Y is the number of hours worked at job B. We should end up with lots of different inequalities here. Okay, lots of different inequalities. So let's write these different inequalities here. Excuse me. So if we had this, we're going to have 4 different inequalities. First one, we need to make sure that she doesn't work more than 15 hours at job A. So her X number of hours needs to be less than or equal to 15. At job B, her Y hours can't be more than 35 hours. Okay, these are going to be a vertical line and a horizontal line. Now we get to our 2 variable equations, and we talk about how much money she can make. Well, she can make $12 at job A, and she can make $10 at job B. And she wants that to be more than $210. That's how much she needs to make at these jobs. And then we need to make sure that her total hours doesn't go over 40. So we say her hours at job A, her hours at job Y need to be less than or equal to 40 hours per week. Well, we can graph all of these different inequalities, okay, a vertical line, horizontal line, and two diagonal lines, and see where they all intersect. That is where that region that has all four different shadings, that is where she can have, she can actually do this job. Okay, lots of different possibilities here, but graph all of them and see where they intersect. Okay, and here's the last one that you can try out on your own. Very similar. Okay, so try it out for yourself. Well, I hope this is helpful for your homework and for studying.